Welcome to Bright Engineering once again. In today's lesson, we'll be talking about electromagnetism. So, what then is electromagnetism? The process where a magnetic field is created by introducing a current in a conductor is what we term as electromagnetism. So, I'm taking it again. The process where a magnetic field is created by introducing a current in a conductor is electromagnetism. So if we have this voltage source, which would have a current flowing right in this direction, and it gets to this particular conductor, would have a certain field generated around this conductor due to the current which passes through the conductor, and this is called the magnetic field, which moves from the north to the south pole of a magnet, right? Now, in our normal electrical circuits, would have something like this, which will be voltage, then a current source, and a resistor, right, giving us Ohm's law V is equal to IR. But in our magnetic circuit, we also have the number of turns times current, flux, and reluctance, which can actually be represented with R or S, reluctance, giving us Ni is equal to phi times R. Alright, now we need to talk about one or two terminologies in electromagnetism. So starting with magnetic flux density. With a symbol of B. We say magnetic flux density is the measure of the strength of a magnetic field. So this measures the strength of a magnetic field, and we say B is equal to the flux on cross-sectional area of a material which has a unit of Tesla T. Now from this formula, B is equal to phi on A, we can get flux, which will be the flux density times the cross-sectional area. When we come here, we realize that flux represents currents in a normal electrical circuit. Yeah, so the electrical circuit would have voltage, which represents the MMF or the force in a magnetic circuit. Then flux representing current in an electrical circuit. Then reluctance also representing resistance. So this is how do I put it? Alright, so that's the relation between the magnetic and the electrical circuit, right? Then we can also talk about another term, the magnetomotive force, which I've indicated here, right? So we say the magnetomotive force, MMF, which is magnetomotive force by This is the force that drives the flux through a magnetic circuit. So we say the magnetomotive force, MMF, which can also be represented with just F, is equal to the number of turns times current. So that will be N times I, and the unit for this can either be amperes or ampere turns, depending on which you want to use. You can actually choose to stick with this, or there's either amperes or ampere turns. All right, now so we've established three formulas now. First of all, magnetic flux density, then the flux, then the third one, magnetomotive force. So we have a few more to go. We can now talk about the field intensity or the magnetic field strength. So magnetic field strength or intensity. This is represented with the symbol H, right? Now we say the magnetic field strength is the magnetomotive force per unit length of a magnetic circuit. The magnetomotive force per unit length of a magnetic circuit. So the field strength H is the magnetomotive force F per unit length L of the magnetic circuit. So this is F, or the MMF, right, on the length, and this can further on be expanded to Ni over L, since force can be expressed as number of turns times the current. Now I would have to talk about relative permeability. So relative permeability is just the ratio of permeability of a medium to free space, right? The permeability of a particular medium to the ratio of permeability to the permeability in free space. So relative permeability is also denoted with mu r, right? Mu r. Now, mu r is the permeability of a medium, or absolute permeability to permeability in free space. So this is permeability in free space. Then this absolute all right, so we can then find absolute permeability to be the product of relative permeability by permeability in free space. Now in free space, we say that relative permeability of a material is equal to 1. In free space, relative permeability is equal to 1. So in free space or vacuum or air, relative permeability of a material is equal to 1. Now the magnetic constant, permeability of free space, right, is also equal to 4 pi times 10 power negative 7 Henry per meters, right? And sorry, I forgot to talk about the units for the magnetic field strength. So if we are using amperes for the force, this will be amperes over meters, right? And therefore the unit for this is ampere per meters or ampere turns per meters, depending on what we are either choosing amperes for force or ampere turns for force. So now we can also express relative permeability as the density on intensity, magnetic flux density on the magnetic field strength or intensity, right? So this can be expanded as mu naught mu r on bh, but in free space we know that mu r is equal to 1. Therefore in free space you can say mu naught is equal to b on h. Now let's talk about reluctance. So any magnetic material has a certain amount of reluctance, which is just the opposition to the magnetic circuit offers to the passage of magnetic flux, just as resistance offers opposition to the flow of current. Reluctance also offers opposition to the passage of magnetic flux. So the opposition that a magnetic circuit offers to the passage of magnetic flux is what we term as reluctance, right? Now reluctance S. So reluctance can be denoted by S, or in some other theories they also use R to denote reluctance. We would be using S to denote reluctance here, and this reluctance can also be said to be the ratio of the MMF applied to the flux induced. Thus the ratio of the MMF applied, the force, to the flux induced, right? So if we did V is equal to IR, and we said V represents MMF or F in a magnetic circuit, then I stands for current, or I stands for flux in a magnetic circuit, then R stands for reluctance in a magnetic circuit. We can say that F is equal to flux times S, right? F is equal to phi times S, which will then give us S reluctance to be the force all on flux, right? Now this formula can further on be expanded, where we know that F is equal to the N times I, and flux is also equal to B times A, or F can also be HL, where flux is BA. So depending on the kind of question or application you need to do, you can use either of these expansions, right? Let's say you want to find the number of turns and you have these parameters available, you can just use this one. Or we are supposed to find length and you have these ones, you can just use this particular formula. Now working more on this HL and B, we know that mu is equal to B on H, meaning we can have B to be equal to mu H, right? So when we put this, let's say equation 1 into S, right, into S. So equation 1 into equation S, I don't know whether that really exists. Then we can say S is equal to HL on B A, and the B is now mu H. So mu h times a. Then h cancels out. Then we can have S to be equal to L on mu a. Therefore, reluctance can also be said to be the length on absolute permeability times cross-sectional area. Alright, so the unit for reluctance is also Ampere per Webers, right? Ampere per Webers or Ampere times per Webers, where Webers is the unit for flux, right? So if I forgot to say that, flux is going to be, and its unit is Webers, right? That means if the unit of this is amperes and this is Webers, we then have amps per Webers as the unit for reluctance. Alright, so continuing with this small circuit, we can summarize everything on electromagnetism, where this is, let's say, an ion core, right? An ion core, right? So this ion core has this turns being wound around it, right? And when current is being passed through this turns, right, which is N, a force will be generated, right? So the force which we said is equal to Ni will be generated once we pass this current through this turns, right? And this will then induce a flux which will flow through the coil, right? And this just indicates the mean length of the coil. That's when we find the circumference of the smaller circle here and the bigger circle, and we find the mean of the two answers. We have the mean length, and this, in magnetism, we always deal with cross-sectional area. So this particular space is the cross-sectional area, right? Which if the core is more or less a rectangle or a circle, you just need to find the area of that cross section, right? So thank you. I think this should give you a brief idea about magnetism, and please kindly like, share and subscribe. Thank you.